3. Okay, good evening and thank you for joining me right now. We actually had some interesting stuff in Alaska just yesterday, actually into today. In fact, let me take you right now to 7 days all magnitude, or it's not all magnitude, 2.5 magnitude plus. And we had quite a scare. We actually had a 4.5 earthquake that hit Alaska. 14 felt reports, and in fact, this earthquake triggered the AVO to raise the status of this volcano from green to orange. Look at that. So, okay, let's look at AVO. I'm going to take you to the Alaska Volcano Observatory. Actually, that's how I knew that something happened. It wasn't through any website. It was just looking at this. This is actually how I found out that something interesting had happened. It was actually when I looked at the USGS, I saw that little swarm, well, actually aftershock sequence. It was likely a fault or earthquake. I looked at this spectrogram plot on swarm, and this was actually the main shock here. I don't know if this was the, oh great. No. Look at the, great. Hold on there for a moment, just need to reload that. Okay, so let me look at swarm again. So you had the earthquake that occurred, so you had a 4.5 that occurred at 21:16:49 UTC, which is Universal Coordinate Time, which is basically Zulu time. In the UK, it was basically 9:46 p.m., which is almost 9:47. Actually, no, 9:17 p.m. So it's using military time or 24-hour time. So then now let's look at swarm again. There. So this was not. This is actually the aftershock sequence likely. This was on the 16th. Let's look. See when that happened. It was the 15th. So this happened the day before. This was 15th Greenwich Mean Time. And let's see if this uses local time or mean time. This, I believe, is using GMT possibly. Oh, there, the 14th. Okay. I'm trying to see if I could find anything for the 15th. There we go, the 15th. This is the big one, guys. This is the big kahuna. This is the main shock right here, the big guy. Right here, come on. Come on. And, oh God, still, okay, I'm still getting some problems, right? I'm trying to look at swarm. That was the 4.5. As you can see, there was almost no precursor activity. There's no harmonic tremors. Basically nothing that signify that this would be some sort of major event. So despite a lack of harmonic tremors, I mean, we just had a tremor right now. It was just an earthquake. There was a little one there. So there's definitely earthquake activity, don't get me wrong, even though they're only showing some stuff. No, okay. Yeah, Swarm is a little glitchy right now because this computer is a little, I don't have the best internet connection. I have Spectrum, which is, well, it's not Spectrum, it's the Wi-Fi, because I'm using the Wi-Fi. I'm not using the direct connection. So it's a little bit glitchy right now. So it's going to take some time for the program Swarm to load. I prefer doing a live stream because it's just easier for me to get everything collected. There we go. That's the big swarm, okay? Just want to make sure. No, come on. Yeah, it's a little slower. Let me check the internet speed. Okay, looks like it's good. No wave data review. Okay, looks like I can't basically find anything. So, might have been precursor there. I mean, it definitely looks tectonic to me. not truly a volcanic. This does not look like a volcanic earthquake to me. This is right near the Makushin earthquake. Makushin Volcano basically is very close to where this earthquake occurred. This is where the Makushin volcano is, like basically right over here. So very close to the volcano. That's what 1 day on magnitudes. You had a 3.3 that happened basically just a few hours ago, and you had a 0.9 that occurred at 8:59 UTC, also on the 16th. They're not showing anything recent. Like, they're not showing anything else, despite the fact that there's numerous earthquakes here. Okay, just reset that again. I'm gonna close it out. Keep in mind, some of these seismic stations are very sensitive. They could even pick up maybe negative earthquake. So these are some very fine-tuned instruments. This volcano is considered to be a high-risk volcano. So this is, I'm going to open up Swarm. Even though it looks all funky, it's actually pretty stable when you look at it. This is just that the instrument is a little wobbly, so it's showing up on the Webley corridor. It's a little bit wobbly. All right, so I'm gonna right click, see if I could get the spectrogram plot. Okay, might have to close it out and restart it. Yeah, I'm getting some. Alrighty, let me try this one more time. I don't think there's any danger from the volcano, and I very likely believe the volcano will go back to a... There we go, finally, yep. This is one of the latest earthquakes. Probably time here was 8:40, there we go, 8 something. 8:35, 8:40 UTC. And latest earthquakes, 1536, 9 point. So this is basically this one right here. It's probably that earthquake. They registered as a 0.9, 8:59. It was an 8:40. Let's look at the time again. Let's look at the timestamp. It was right around 8:40, 0840, which is today. This is actually now. This is what's happening right now. Well, actually, this was in the morning. This was, let's see, 0840 16Z. Let me see if I could maybe go a little further back. So maybe, let's see. Can I find that? That, I can't really seem to find that earthquake. Looks like they, maybe 70s old magnitude. Let's see if I could find it. It was, maybe it will be viewed as the 15th or 16th. Let's see. Nope. Surprised they didn't. Maybe there was another earthquake. Maybe it was this one. Nope. Can't find anything. I'm zooming out, and really there's nothing. Let's see. Unknown. Maybe that was it. Maybe that was the one. Nope. USGS is not registering it. The only one the USGS registered. Let's go to the 4.5. The 4.5 that occurred. Let's go to 2.5 magnitude plus. So the USGS did not register that one. So because UTC, they're using UTC. And look at this. Look at this here. Also, this is also UTC. Greenwich Mean Time and UTC are both the same thing. In fact, let's go to Google and find out. UTC time is Greenwich Mean Time. I think it's the same time. It's often interchanged and confused, but GMT is a time zone. UTC is a time standard. UTC, but a time standard for the base of civil time. Universal coordinated universal time. And of course, it's always 4 hours plus. So this is always GMT. The AVO always uses Greenwich Mean Time, aka UTC time. You know, they always use GMT. So in fact, this earthquake right here happened at 8:40, 808-40-25 UTC. And there's no earthquake I could find that matches that. There's just none. Major, I mean, that's a pretty good sized earthquake. Maybe magnitude 2, magnitude 3 earthquake. Frequencies, though, are not that low. I mean, this is not a very low frequency event. This is a mid to high frequency event. So you could look at the power. See, it was up to 10 to the 7th power, not too high. Definitely, there's some pretty impressive. Great. Great. What just happened there? How that happened, but yeah. All right, let me close that out again. Let me go to yesterday. See if I could open up Swarm. Could open up the. Looks like no, I cannot. Let me open that again. I don't have too many windows open, or I'm worried that the computer could crash. Let me make sure that. Oops. Okay, let's. Yeah. Anyway, let me look at Swarm again. It looks like this is not working. Okay. Okay, alrighty. Close that out again. Just wanna make sure my video live stream is still working. And yes, it is still running. My live stream is still working. Volcanic eruptions are not really registered in. Sure, sounds working. Volcanic eruptions are not really registered in Richter scales. Sure, sounds working. Yeah, volcanic eruptions are not registered in Richter scales. They are registered in the VEI, which is the Volcanic Explosivity Index. The VEI, or the Volcanic Explosivity Index, is a measure of how powerful a volcanic eruption is. VEI 5 is basically 1 to 10 cubic kilometers of magma. 10 to 100 cubic kilometers is considered a VEI 6. 100 to 1,000 cubic kilometers, or up to 400 or up to 250 cubic miles, is considered VEI 7. Anything above 999.9 or anything above 1,000 cubic kilometers is considered VEI 8 or is a super eruption. Even VEI 7 could be considered a super eruption. And the last time a super eruption, or at least a VEI 7, occurred on Earth was in 1816 with the eruption of Mount Tambora. And before that, we also had a supervolcano that erupted. We had the Taupo Caldera. The Taupo Caldera in New Zealand, Lake Taupo, had a VEI 7 eruption about almost 1,000 years ago, about give or take a few hundred years. There was an eruption that was called the Hecate eruption that occurred on Lake Taupo. The last time a hotspot supervolcanic eruption happened, those are very rare. Most super eruptions, including Tambora or Lake Toba, and numerous supervolcanoes around the world are caused, or the same type of volcanism that causes stratovolcanoes. It's subduction driven volcanoes. Subduction volcanism is actually the most dangerous form of volcanism. Hotspot volcanism is incredibly rare now, but it also used to be very dangerous, not because of super eruptions, but because of flood basalts. And the last mass extinction was actually because of a flood basalt. It changed the climate by releasing so much carbon into the atmosphere that it changed the climate on the Earth by releasing, over a period of several hundred years, as much CO2 as we're releasing now, and it caused a mass extinction event. But the release was even bigger than what we're doing now. And yes, humans are causing climate change. We are definitely contributing to why the level of CO2 is increasing in the atmosphere. Even with the coronavirus pandemic shutdown, the amount of CO2 that we're pumping has reduced, but we're still pumping CO2 into the atmosphere. So you're going to say conspiracy theorists say, oh, see, why is CO2 still increasing when our emissions have dropped? The emissions didn't go negative, just the rate of increase. The rate of increase has lowered, but the increase is still happening. So, for example, say the increase is, instead of going like this, the increase is a little less, but it's still increasing. You're just reducing the rate of increase. You're not going negative, you're going negative on how much you are increasing. Negative, like, okay, so this is zero emissions here. Zero emissions is at the bottom of the screen. So we're pumping this much, but we reduced how much we're pumping. And in order maybe to cause a net change, your emissions might have to be down here, not merely a little downward trend in increase. So you're still increasing the amount of CO2 in the atmosphere, it's just the rate of increase has went down. Just put it out there for people who think that we're not pumping CO2 in the atmosphere, that the coronavirus has all of a sudden stopped all CO2 emissions. No, it has not, and we're still increasing CO2. But yes, the rate of increase has slowed down. Between 2018 and 2019, Mauna Loa has registered up to almost 3 to 3.5 ppm increase. This year, over the same time frame, it's about 2 to 3. So a good percentage lower. So that's something to keep an eye on. Maybe we don't need, lockdowns to lower emissions. This is because of the pandemic. We actually need green energy, nuclear energy, more investment in the renewables. But let me see if Swarm has opened up. And also, using volcanoes to cool down the climate is a very, very, very bad idea. Because look, you're going to cause a lot of problems due to, okay, that was a distant earthquake. This is definitely distant. Yeah, that was probably the one off of Alaska. You see very low frequencies, definitely symbolizes a distant earthquake. I believe that was this one right here. This one, I believe it was that one. Yep, 4.0 right here. That's a 4.0 that I'm picking up there. About 2159.07. Yeah, the seismogram picked it up at 2159.40. So about 20 to 30 seconds after the earthquake hit. About close to 150 miles away, probably. So right about 21, this is when it started. So the first waves did hit at 21, let's see, right around 2137, and right around 2137 to 38, and the earthquake initiated, according to the USGS, at or around 2107, so 30 seconds. So you want to look at how fast seismic waves travel. Waves travel. So kilometers per second. P waves. So this is the P wave arrival right here. Actually, you know what? Let's look at the shaking. Let's look at the arrival of the P and S waves. P and S wave arrivals. And I could basically, just using that, I could tell you how far that earthquake was from that seismic station, just by looking at that. So that's the epicenter at 137 kilometers southeast of Akutan, and Akutan is right around here, so southeast of Akutan, that's right around there. So now let's look at PNS wave arrival. Okay, that's P wave, that's S waves. No, that's power. This is P waves. And the S wave, so that's P waves, and then the S waves. So you had primary waves here. The S wave arrival is right around 22 minutes. S waves and then slowing down. Let's look at seismogram again. Again, P wave, P wave, P wave, and S wave arrival. That's the S waves arriving here. So it's all P, 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 then S. So P waves arrived right around here. So let's see when the earthquake initiated. This is the initiation of earthquake. And let's look at the time. So about 30 seconds. 30 seconds. P wave speed. P wave speed. 5 to 8 kilometers a second. So let's average that out. 5 plus 8. Average that out to 6.5 kilometers per second. And let's do the math. 6.5 times 30. And then we could do that in miles. If you want, I could also do it for miles. Let's open up let's look up the calculator app and let's do the calculations. So 6.5 times 30. 195 kilometers. So that is about let's look at that's about 140, 130 miles away. Kilometers to miles. Actually, let's look at, should be no, not even 140. It should be about in the low hundreds. Actually, no, it's about 2.2, so it should be about 120 to 130 miles away. Yep, 121.161 miles. But let's look at the formula. Convert kilometers to miles. Of course, yeah, it's much better to use the metric system than it is to use the imperial. Metric system makes a lot more sense. Soon it's going to take, it's used in medicine, it's used in, and now it's, I think it will be soon being used in the military. Even in my game, Ace Combat 7 that I play, almost everything there is metric system. Yeah, it used to be imperial, but now it's metric. I think you could change the settings, but I'd rather use metric, but it's just confusing because the speed, I'm so used to everything being in miles an hour that, okay, the stall of speed is, do airliners use metric or imperial speed? Do airline knots, miles, not miles an hour. Yep, airplane is measured in knots, so not kilometers an hour, which means it should not even be miles per hour, it should be in knots, nautical miles. Which system is I think it's metric. Yeah, imperial actually. I think in Europe they use the imperial. I think they will transition even in the United States to the imperial system, a metric system soon. Okay, let's go back to Swarm. So this one is definitely Alaska. This is here. This is definitely here. And let's look at the frequencies. Yeah, So there is a bit of a harmonic tremor. There's some lower frequencies, higher frequencies. Let's look at here. This is, yeah, there's low frequency tremors. I want to see if this was before. I don't know if this has to do with background microseisms or has to do with the whole aftershock sequence. But it's low frequencies. You do not want to see high frequencies, especially with harmonic tremors. Higher frequencies mean that an eruption could happen, especially if the frequencies are jumping up like that when you're looking at a spectrogram. With earthquakes, low frequencies usually means magmatic fluids. So here you go. So nope. I want to go to yesterday and look at that. Okay, let's click out of there. Okay, let's go to yesterday. Okay. I'm having some trouble using a swarm for yesterday. There we go. I'll look at the earthquake. That's where the earthquake happened. Yeah. Yeah. See, no wave data. No wave data. I'm having trouble accessing that data there. And that's what I'm trying to look at. I'm trying to see if that happened from before or after. Because even earthquakes, even in non-volcanic areas, could cause a lot of background activity from the earth just like settling down from like just maybe the background vibrations or other stuff as well. Okay. Let's see. Okay. This is before the earthquake. Looks like this is just background microseisms from oceanic activity. Nothing to do with volcanic activity. Yep. So that was before. And so yeah, this is the aftershock sequence, is there. Okay. Now let's reopen that and see if anything has changed. Has there been any harmonic tremors ongoing at the volcano? And I have not seen any indications of that yet. No harmonic tremor activity has occurred at the Makushin volcano. So there's no major concern. I'm not seeing any harmonic tremors. Like, look, I'm gonna look at this right now. There is no harmonic tremors going on. In fact, the seismogram looks pretty normal to me. Like, okay, I'm gonna close that out again and open it up again. There's like some background, maybe some minor aftershock activity. Like there was a small, okay, yeah. Okay, let's look at that. I'm just gonna look at the data right now and I'll tell you what's going on. There's just so many volcanoes to look at. I mean, Cleveland had a minor eruption. The last eruption at Makushin was in 1995. It is a stratovolcano nestled inside a caldera. So let's open this up and look. Okay, I'm trying to. Yeah, I'm having some difficulty. It's just that, yeah, see, it's loading. It's just taking its time right now. Yeah. All right. So let's. So thankfully, nothing is concerning is going on at Makushin at the moment. And the earthquake wasn't truly over the volcano. It was 10 to 15 miles east of the volcano where the strongest earthquake occurred. So right now I'm saying this could be volcanic tectonic activity. This could be that magma is starting to rise. Still no harmonic tremors, which means that the magma is pretty deep on the ground. But as the magma gets closer to the surface, you might start seeing some harmonic tremors. You might start seeing more, higher frequencies. And in fact, I could show you a harmonic tremor, what it looks like on a spectrogram plot. Harmonic tremor spectrogram. Let's go to images. This is what a harmonic tremor looks like on a spectrogram, just right before an eruption. That's a harmonic tremor. And there, that's frequencies increasing. That's not magma rising. Those are frequencies that are increasing as the hertz go really high. And look at that. That's the eruption. And this was this is, I believe, the Cleveland volcano, if I'm not mistaken. Let's see what they're saying. It was, let's see what volcano that was. Listen to the stream, sped up to 60 times. And, oh great, doesn't work. Apparently, I mean, this is from 2011, so that's basically a volcano. You know, basically, this is hertz. So, and let's look at this. High frequencies are basically not good, especially if it's like this. I mean, this isn't hertz. This could be a different kind of a spectrogram. Like, here's the thing. Let's look here. No harmonic tremors. I mean, this could be my background microseisms here. From ocean waves crash, you can almost see like rhythmic patterns of ocean waves. Boom, boom, boom. Ocean waves. Here, earthquake, earthquake. Aftershocks here. No harmonic tremors at the moment. Everything is just background microseisms right now. There could be a little bit of a tremor there. I mean, it could be related to weather. But look, earthquake. But a harmonic tremor is going to be a continuous earthquake that just will not stop, basically. This just continuing non-stop. Basically like this, but continuing non-stop. Just, especially up here. This activity just will not stop. So, basically, and then as the frequencies get stronger, as the ground shakes faster and faster and faster, so right now I'm not seeing any indications of an impending eruption. Nothing that should be concerning. Frequencies are normal. Yep, everything seems to be fine right now. Yeah, aftershock, 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 aftershock. A little aftershock right here. A little one, huh? And maybe a tiny one there, just tiny, barely noticeable. A little one there. Could be either from the one in Alaska or the one further away. And that's the earthquake here, guys. This is the one that just hit Unalaska. I mean, off the coast, 120 miles to the southeast of the volcano. So, right now, activity seems to be... Oh, great. Ugh, how did that happen? Again, distant earthquake. I don't know how I got to the 14th, but... let's look at here. That's an earthquake, the P waves and S waves. Alrighty, let's look at that. So normal, nothing to be concerned about. So with a volcano, lower frequencies are frequently associated with the fracturing of rock, while harmonic tremors is the movement of magma. So low frequencies, like this, especially if it's dominantly low, means that rock can be breaking, or it could also mean that the earthquake is further away. But if it's close and you're having dominantly low frequencies, that could be a little bit concerning. And the frequencies are dominantly low. Like, there are definitely lower frequencies. I mean, look at this. As you can see, the dominant frequencies are from 0 hertz up to 13 hertz. So the most dominant frequencies are up to about 9 hertz. So you have definitely some low frequencies. Look at that, 1.97 there. And then the coda drops off. Basically, there's P waves, the S waves arrive here actually, not over here. This is the P waves. This is the primary waves here. This is before the secondary waves arrive. As you can see, P waves, and then there we go. Here's where the S waves arrives. Okay, let's zoom in a little more. The P waves and the S waves arrive right around 8:40, like 29 seconds. So 28 and 29. Let's look at frequencies again. Dominantly low frequencies. Let's get out of there and let's close that out and go back in. And this is not the main shock, by the way. This is the after. These are all aftershocks, and these are, I would say, pretty substantial aftershocks. I mean, magnitude 2 to magnitude 3 aftershocks. I mean, this one should be maybe at 0.5, maybe. It's weird. I think yeah, zoomed in too much. Let me close out and go back in. There we go. Very, very weak. Wow, that's probably further away. That's a very weak aftershock. In fact, I hardly see any waves with that. To zoom all the way in. Doesn't look like an earthquake. I mean, I don't know why that's happening. That's weird. I mean, it's weird. Oh, great, let's have that. All right, guys. I mean, weather's usually my thing, so yeah, this is definitely on the island. There's no doubt this happened on the island. Let me... There we go, aftershock, possible aftershock. Right around 5 minutes ago we had an aftershock. Another one here. So background activity is normal. I mean, besides some of those stronger earthquakes, some lower frequencies here. Righty, and let's go back. Okay, let's look at other eruptions. Let's look at Cleveland actually now. Let's look at Cleveland. Let's close this out and look at Cleveland because they're saying that Cleveland was actually an eruption, a few days ago. And looks like Cleveland I cannot find. Great Sitkin frequently has activity. It's one of the more active volcanoes in Alaska. Let's see if we can find any drumbeat activity there. I mean, I know Mary Greeley said there was some drumbeat activity in Yellowstone. Drumbeat, that could have been a drumbeat, but yeah, kind of zoom in really strong in there. Oh, come on, this won't load. Okay, no good. Nope. Looks like Cleveland. Great Sitkin has a lot of seismic stations. I mean, that is many seismic stations. GSCK, GSCK-BHN. Look at GSH. Okay, make sure I got it correct. GSCK-BHN. BHN. Yep. Let's look at the coordinates. Yep, Great Sitkin volcano. So it's related to the volcano. Ooh, we have an earthquake here. Let's see what its frequencies are. And is it low? Wow, P waves, S waves. Yep, P waves, P waves, P waves. S wave arrival about 9 seconds after the earthquake started, which is about normal. Let's look at the frequencies again. Seem to be pretty far away, not too close. If that's on the volcano, that means that, yeah. Let's look here. So 4, and it looks a little noisy. Okay, yeah, definitely. There's definitely some background activity going on, but nothing too like worrisome. Okay, looks like Great Sitkin is in good condition. So I can't find Cleveland. Yeah, let's close out. Oops. 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 basically close swarm out. Oh wait, all right, I'm gonna swarm up again, and here we go. Open files. Great. Yeah, what have I done? Help. Okay, come on. Oh. No, oh gosh. Open file. No. Close files. You know what? I think it's better if I just close out Swarm right now. And open up. Okay. Great. Just great. Windows Phone 2.8, 2.8. Ah, there we go. Winston, that's still there. Yeah, I'll have to. Let's go again to Makushin. Let's go back here. That's a global seismic network. This is local. Let's okay. Close out and go back into it. MCIR. So far, nothing. Little tiny aftershock. Tiny, tiny, tiny. I mean, I don't know how to open up Yellowstone. I mean, yeah, I really do not know how to look at Yellowstone. I will need to talk to Ben Ferriello because he's the person who basically taught me how to do this. All my thanks goes to him. Ben Ferriello is basically the best at this. I mean, I don't know how to look at Indonesians because a harmonic tremor looks more like for example, let's look at, I'm going to look at Magma Indonesia. Of course, I cannot use Swarm with it. I'm just going to look at Magma Indonesia, and I will basically show you various seismic stations and their web recorders. I don't know what that is, but there's drumbeat activity. But let's look at the time. This could be mining activity. Yep. Okay, that's nighttime, guys. This is nighttime. Wait. Okay. Of course, this is Greenwich Mean Time, I believe, right? Yep, that's GMT. It's definitely Greenwich Mean Time, not local time, right? Yep. Basically, night and day is flipped at this location. So night, 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 day, 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 of course. It's currently day in Indonesia right now, about 3 p.m., I believe, if I'm not mistaken. Let's look at Bali local time. 3:07 p.m. Yep. Exactly 12 hours behind. Exactly 12 hours behind. So, yep. So basically, this is 6 hours behind. That's one. So this is when that mining activity starts right around this time. So 23 hours. Let's go 7 hours back. That will be. So this would be one. Let's go by hours. So this is 7 8 p.m. So this is some earthquake activity here. This is harmonic tremors, guys. This is harmonic activity here. This is what harmonic tremors look like. Harmonic tremors, mining activity, earthquake, harmonic. That's not harmonic tremor. That's just an earthquake. But let's look at other seismic stations. and I can basically show you what's going on there. Okay, G'day. Slamet. Yep, Slamet has just been having a lot of like this activity. Just a lot of just harmonic tremors and earthquakes. I mean, look, the last eruption in Slamet has not happened since 1999. The Slamet volcano, Mount Slamet, my bad, 2014 was the last eruption. It is a stratovolcano, not very explosive though. But yeah, this is volcanic. Like you can see, it's just pockmarked with just minor volcanic tremors, just pockmarked in the whole crater. I mean, this is definitely harmonic tremors. Like you can tell, there's just minor harmonic activity at all times. It's just covering the whole area. I mean, there's, and then look at this. This is not normal earthquake. This is harmonic tremors. There's like a lot of magma there, but mostly a lot of gases in there. Keep in mind, Slamet is a stratovolcano. It's very active. So this is a very active volcano here. It's not notoriously dangerous. It doesn't have explosive eruptions. In fact, Slamet volcano discovery. In fact, let's look at it. It's yellow. 2019. Of course, and over 50,000 earthquakes. Gas emissions with steam plumes rising 300 meters above the crater, rising hot spring temperatures, and emergence of seismic tremor, which is still going now. A 2-kilometer inclusion zone, silent explosive. Eruptions very frequently erupts. Of course, Tal volcano. Let's look at Tal right now. Let's go to Five Oaks. The OST. Let's look at their Twitter. Let's look at their last June 15th. It's recent one. So let's look at the most recent one as of, I think. Wait, is it still back to 0? It's still level 1 normal. Let's go to around 8. 5 hours. I think I should go 7 or 8 hours back. Let's see. Okay, there we go. No. Wow, I'm surprised. They didn't post anything on Tal. Usually they do. Nothing for the 16th. Yeah, wow. They haven't posted. Oh, wait, there we go. It's usually, yeah, June 15th at 8 a.m. They haven't posted in a while. 2 volcanic earthquakes. Nice. Looks like Tal's finally calming down. I'd like to see that. I'd like to see that. Finally. Even though it's maintained, I mean, looks like the volcano's finally settled back down, so may not erupt again for anywhere from a few months, maybe a year or so. But my concern is that it still could have a major eruption eventually. I haven't looked at Tal in a while, in fact. 6 volcanic earthquakes, okay, on the 14th. It looks like they may have, if they haven't done anything, maybe there hasn't been anything on the 15th. 6.1 or 6.7. Let's look. U.S. U of U, Yellowstone. Seismograph stations. That's the one I was looking for. Alright, so 2017. That's something I'm not used to, actually. No, I'm like, where's the seismic stations that used to always be here? Okay, that's a little normal. Monitoring, I think that's the one. Live seismograms. There we go. Good old life seismos. Let's look at borehole, or no, borehole. Let's look at YLT, YW network. What? Live seismogram? Come on, give me the web. There's nothing concerning here. Nope. Nothing concerning at all. Nope. Nothing concerning here. Nothing concerning here either. It's probably just some background noise there. Nothing there. And let's look at Norris. This is Norris. Let's look there. An eruption in Norris, and cannot find it. Looks like I'll have to use it to temp. USGS Yellowstone monitoring. I mean, there's always volcanic activity somewhere around the world. There's several concerning volcanoes that I'm actually concerned about. They're actually mostly in South America, if you believe it or not. That's the one. Wait, which one was the? See, wait, guys, that's the one I was looking for. Let's look. Eruption on the eruption. Okay, that was not an eruption. It was just a spike in temperature. Eruption. Yeah, that's a little weird. Let's look in the past. Nope. Let's look at. No, yep. Let's look at the past 30 days. Eruption May 19th. Possible eruption on the 22nd. Here, we got an eruption here. That was not an eruption. Possible eruption. That could have been a little one. Eruption. But last steamboat geyser eruption. Let's look at the. Yep. I'm going to do a little weather update right now. We're going to do a sea surface temperature anomaly, SST anomalies. Let's look at ENSO right now. Current anomaly charts. Let's look at for which location. Yeah, see this here? Aha. There's even an La Nina-like pattern developing. I have never noticed this before, but there's a possible ENSO-like pattern developing, a possible La Nina type pattern developing in the equatorial region. Look at that. What will this mean for this year's hurricane season? What will it mean for the Saharan air layer? What will all this warm water do? I mean, this is what you want to look at. Will this fill in? Will this warm up or cool down? Or how much of an impact this will have? So let's look at 2005. SST temperature anomalies. Let's look at 2005. Let's, especially around this time. So June 18th. So you had very similar. Look at that. Look at that. So very similar. You had a La Nina developing off of Africa. Very similar to 2005. Look at that. Warm here, cold here. So look at that. It's almost a repetition of what happened in 2005, guys. This is very concerning, especially with very strong La Nina here. I mean, we are having a very strong La Nina right now, guys. Let's go back. Change regions. I actually don't want to look at full global right now. I kind of want to zoom into the ENSO region. Yep, looks like I can't access it. No, this is not what I want to look at either. I want to look at sea surface temperature anomalies. Okay, come on. Yeah, but very warm water temperatures here, though. So you can still have hurricanes forming because of the warm waters there. So let's look at Nino 3 right now. Nope. So we're having a very strong La Nina from Nino region 1 and 2 all the way to 3 and 4. So very strong La Nina developing here. The surrounding waters are still pretty warm, so this is not a very strong La Nina like what happened in 2010, 2011. That La Nina was incredibly strong. I mean, let's look at 2010. We can also take you to 2011. Let's look at around this time, June 2010. Wasn't that strong, but then look what happened towards the end of 2010. Boom. Incredibly strong La Nina. Look at this. The entire Eastern Pacific, the Gulf, the Atlantic, all of this was just cold. And just one big blob of just cold. Like, you had warm, you basically, and that's what caused the big temperature drop in, well, let's look at global temperature anomalies. Let's look at Dr. Ray Spencer's, of course. That's what caused a little drop here. Oh, look at that. 2010, still increasing. Was there a decrease? Let's look at Dr. Roy Spencer. SST anomalies. No. Let's look at May 2020 global temperature anomaly. Oh, look at that, Dr. Roy Spencer's. One of the global lower atmosphere. So, global lower atmosphere includes the entire troposphere. The lower atmosphere is anything from the tropopause, everything down to the surface. And let's look. 2010, 2011, there you go. Was that La Nina? So we're gonna have a La Nina. So yeah, you can have a little bit of a drop. But look, the solar activity didn't really have to do much with it. You still had an increase here, right in 2010, big increase. I mean, you could say it was because of solar minimum all you want, but trend's still going up. We're having 2 cycles of very weak solar activity, and look, having no net effect on reducing global temps, guys. Look, it's not. It's increasing. Look at this. Look where the average used to be. Just follow the ladder. Just follow you could almost draw like a line. Just almost trying to go exponential here, guys. Like, you could just start to basically draw that little slow. Warming's kind of starting to increase, guys. I mean, yeah, you're going to have a decrease. So it's not going to be boom like this. It's going to be more like, and then eventually it's going to increase as once the sun goes back up to normal, once the temperature catches up with the CO2 and you're going to have some feedback warming, you're going to have a more accelerated warming, guys. You're not going to have a slow down of it. You're going to have an accelerated warming. Guys, we need to do what we can to lower carbon emissions immediately, and not only lower them, but to reverse the carbon we pumped into the atmosphere back down to what it was about 50 to 60 years ago. I'm not saying we have to go down to pre-industrial levels. No, we don't. But we have to decrease it enough that we won't cause a catastrophic climate change to this planet. There's already catastrophic weather events going on just because of, well, normal weather events, but it's already being exacerbated by global warming. It is. Like, we're having global warming. Climate change is basically natural variation of climate. This is anthropogenic climate change, or even more accurately, anthropogenic global warming. The reason we call it, where scientists call it climate change, is because you have some areas, oh, look at this, United States, it's a little cooler than normal at one point in 2020, but the rest of the world is mostly warm. Look at all this warm stuff here. There's a few isolated pockets of blue. April 2020, May 2020 was abnormally cold because you had a polar vortex that came down. Why did the polar vortex come down? Let's look at the NAO, and I'll show you why that happened. Let's look at May. Oh, right when that happened, boom, the NAO crashed. That's what's caused the record cold and snow in the Northeast. Yeah, those freak snow squalls that hit New York and upstate New York on May 9, 2020. You had a negative NAO. Well, it was neutral for to positive for almost the whole winter. Why? The winter was so warm. No blocking. And let's look at the Arctic Oscillation. Oh, it was also slightly negative. Let's look at the PNA, probably positive to negative, neutral to positive. Yep, it was positive. The AAO, it's been mostly stable, and that means that Antarctic sea ice is going to start to become positive. NSIDC, let's look at that. Let's look at our Arctic sea ice. Let's look at that. Yep, exactly as I stated. It's going to be increasing because you're having a positive AAO. You do not want to have a negative NAO. You definitely do not want this to happen. No, I really hope that's wrong, because that is going to cause a major crash in Antarctic sea ice. Yeah, that's not good. You really do not want to see that, especially in Antarctica. You really don't want to see that. Ooh, guys, you really do not want to see that. Because that's probably going to cause a good substantial crash. May even end up being over here. Yeah, because that's going to, a flip from positive to negative is going to cause probably low pressure systems to basically collapse. And basically it's going to, what that's going to do is basically going to cause major variations in low and high pressure, and that will cause the pressures to lower, storms to form, and major disruptions of the ice pack, which will cause it to go back to negative. In fact, let's go back in 2019. It was all over the place, and look how low it was. I mean, I remember how we were hitting records just a few years ago. That's because the AAO was mostly positive. So it supported a very strong ice pack with a very strong, very strong Antarctic vortex, or basically you have the Arctic Oscillation, but the Antarctic Oscillation was very positive. Well, you don't want it too positive either. You want it to be stable, and a stable AAO supports a strengthened pack of ice. So if you have a strong AO, but a consistently strong AO, it would strengthen the ice pack over the Arctic. We did have the AO be positive for most of the Arctic Oscillation to be positive for most of this winter. But it's why you had some increase in sea ice. But even then you had some variations that were going negative, positive, negative, positive. A large reason why Arctic sea ice has been so disrupted is not only because of the warming of the waters, but it's also because that's causing the AO to become unstable. Why was the AO positive this winter? Well, thanks to Reykjavik, the volcano in the Kuril Islands that erupted in exactly 1 year ago today. It erupted June 17th, 2019. Exactly 1 year to this day. Caused brilliant sunsets, in fact, in the fall. 2019. Oops. 2019. Let's go to bed, guys. So let's look at Raycock. When did it erupt? Ah, June 22nd. My bad. It's 5 days off. Yep.
Come on, America. Let's road trip. Straight up to a new Kia.
Okay, let's look at that. Boom. Massive eruption. Definitely VEI4 to VEI5. Yeah, there's a VI5. Boom, that's a VI5 right there. That's a VI5. Let's look. So first you had a small eruption, not too explosive, but like puffs of it. And then, boom, VI5. A continuous plume. There you have the VI5 right there. That's definitely plenty. That's plenty, guys. That's a plenty eruption right there. I mean, they said it was VI4. No, that's probably high-end VI4. But I think what happened was it was a big eruption. But keep in mind, it went into the stratosphere. Like, it was a stratospheric injection. You had the ash plume hit 60,000 feet. And here the stratosphere is at 40,000. So in the Arctic, the stratosphere is actually lower, while in the tropics it's higher. In the tropics, the tropopause is 60 to 70,000 feet, while in the Arctic it's 30 to 40,000 feet. Because it's colder in the Arctic, so the stratosphere, the tropopause, it's lower. That's probably why you had the sulfuric injection, and the sulfuric injection actually worked its way down towards the middle latitudes, even the lower latitudes, like closer to the equator. But it did not go into the southern hemisphere. Most of the sulfur from the Raycock eruption, or the Raycock eruption, stayed in the northern hemisphere. Almost all of it stayed in the northern hemisphere. But there were numerous instances of purple sunsets. I've seen it myself, and it was beautiful. In fact, I actually did a live stream about it. Actually, go to my channel. I'll show you. That's Storm Fan Lover. I mean, I thought it was going to cause a cold and snowy winter, but apparently it had an adverse effect. And it threw a lot of meteorologists off, a lot of weather predictions off. Let's go to the fall. There we go. Volcano sunset. It's one of the videos I made. 2014, 2019. It was definitely purple. I mean,
this is exactly what the sky. Okay, not like that, but there's like a pink, like the whole almost a good portion of the sky looking this way is like a pinkish color over there. I mean, it's obviously because of the Raycock volcano that erupted in June. Yeah, the volcano erupted about 4 months ago. Today's June 24th, so it erupted
October 24th.
Let's see, that's
yeah. I said June 24th. Yeah, I was a little bit confused because I was excited. I was seeing a volcanic sunset. First time in my life actually seeing one. I was too young to witness the Pinatubo volcanic sunset since I was home most of the time. Yes, I remember most of my very young childhood, but I was almost always, all I remember is being in a crib all the time, so. And like being in an apartment and the window was behind me, and I was always like scared of thunderstorms since I was like 2 years old.
July will be 1 month, August will be 2 months, September will be 3 months, 4 months now. So yeah, a good 4 months, and it's still causing beautifully amazing sunsets. 4 months after the eruption. I mean, this is going on for quite some time. I mean, I'm looking over there. It's like orange. There's like oranges and pinks. It's beautiful. Like the whole sky is like lighting up right now. There's not a cloud in the sky today, guys. There's no clouds to speak of. And it's just so unbelievably beautiful. Like, this is incredible.
Yeah,
I thought it's going to be ending like weeks ago, but it looks like it's still continuing. There is still that sulfuric acid in the stratosphere that is causing this beautiful sunset right now. It's just so beautiful. I mean, Ben Ferriello made a video about it, about a picture from a ballpark. But look at how beautiful it is right now. I mean, incredible. I mean, there's even a plane landing right there.
Yeah,
You can see
it was
right
more like
there. There's a plane going to JFK Airport. This is in Long Island. I'm working here in Suffolk County right now, doing some political work, and of course the trees blocking some of the best views right now.
yep. Oh, great. Yep. I was in Suffolk County, basically just handing out leaflets for someone. Anyways, yeah, that's why this winter was so strange. I mean, the AO was very positive because the volcanic sulfuric particles cooled down the stratosphere enough that you didn't have a sudden stratospheric warming event until much later towards the spring. In fact, looking at National Snow Ice Data Center, this actually may be a good thing for Arctic sea ice. Let's look at last year compared this year. Last year, look at that. You had a good size increase in Antarctic ice and Arctic ice because of the good news is that this is going to add to the multi-year layer ice. That's what you want to see. You want to see an increase in the multi-year layer ice. Even if you're not seeing a large increase in the ice pack, like you're not up to here, the fact that the multi-year layer ice is increasing is a very good sign. And it's a very, very good sign that the multi-year layer ice is increasing in the Arctic. And I hope that. So the fact that the multi-year layer ice is increasing is very, very good, and I hope that trend continues. Again, that's the Slamet volcano that has last erupted in 2014. Let's look at all the seismic stations now. Just show you one more time. Okay. Cinnabung, wow, Cinnabung has really calmed down. Yeah, Cinnabung has really calmed down. So I like what I'm seeing there, and you know what? Think next 5 minutes, 10 minutes, I'll be heading to bed. 3:45, I'm getting off. It's time for me to go. Getting late. This is me closing out all these other windows to basically make the computer run better. Just closing all these extra windows here. Yep, just closing all these windows though. Still have a lot of windows open. Wow. Yikes. Yeah. Yikes. Yeah, that's a lot. Many windows. Let's look at 2019 and December. Let's look at there. Oh, you had a positive. Look at that. You definitely had something that supports a positive, a cool winter here on the East Coast. Everything was supportive of a cold winter. Blocking and everything. Look at that. You had this. You had warm waters here. You had a very weak El Nino. So nothing was basically against the cold winter in the Northeast. You also even had good Siberian ice pack in November. That wasn't terrible. It was pretty decent. But that volcanic eruption changed everything. It basically was the right word is, it was basically an unseen factor. It was basically, it changed the whole equation. It's basically changed the minus sign into a plus sign. So you basically had everything that was just set up right, and that one little factor changed everything. And it was that eruption that added all that sulfur into the atmosphere. Because it lingered for most of the winter. It lingered. There was even reports of volcanic sunsets lasting into November, so it cooled down the stratosphere enough, or it cooled down the troposphere enough that polar vortex is very strong this winter. Because yes, the polar vortex is, I know the sulfur actually, it doesn't absorb UV radiation, it reflects it. So the stratosphere actually cooled. Yes. It does. yeah, a cheap and easy way to stop global warming. How about a cheap and dangerous plan to stop global warming? Cheap and dangerous. Yeah. So you can see, guess what? 5 minutes. Okay, so as you can see here, here's what this do. Here's what this does. The albedo increases, so reflection of light, reflection of sunlight. Oh, and that means, and then you have acid rain, the deterioration of the ozone layer. So that's very bad. And you can see though, so light gets reflected back, which cools the lower stratosphere and the troposphere. So those SSW events won't happen, or they could warm up the stratosphere a little bit. And look what it says here. Ozone destruction. Yeah. Pinatubo 91 made the ozone hole over Antarctica worse. I'm trying to do... Yeah. No. I'm trying to look at what sulfur does to in temperature. How it would affect like the lower troposphere. That's what I'm trying to find a correlation. Can't really find many articles. Aha! There we go. That might be another one. Right, pronounced positive phase. Oh, even though it was closer to the Arctic, same effect. Pronounced positive phase. That's exactly what I noticed too. The AO was positive this entire winter. Oh yes. Temperature gradient, strengthening of the equator to pole temperature gradient, because Arctic gets cooler, tropics not them by that much. Okay, to understand. A series of control. Because yeah, it cooled down the tropics, but not by as much as it cooled down the Arctic, surprisingly. Now this is looking at not temperatures, this is looking at heights. Let's look at 91, 92, 92, 93. 91, 92, so normal, nothing too crazy. December, January, February. So you had a stronger AO, but look at that, 92, 93. Very strong polar vortex. So that's the same year the superstorm happened, but that winter wasn't all too cold. 93, 94 though, very cold winter. Yeah, 93, 94. Normally cold winter, but not necessarily snowy. So snowy winters are usually caused by the pronounced negative phase of the Arctic Oscillation combined with the negative phase of the NAO, caused by and also combined with a positive phase of the PNA. It's basically what you want for major snowstorms along the East Coast. If you want major snowstorms, do not wish for a volcanic eruption. Or if you do want, volcanic eruption, hopefully it's not too large. It's gonna like destroy the ozone. Like you want, to reduce global temps, right? But you don't want to destroy the ozone. Then lower CO2 emissions. That's all I'm gonna say. Stop cutting trees down, start planting trees instead. Thank you all for watching and have a great day.